In this video, let's run through the last 5 calculator multiple choice problems in our series on the released AP Calculus AB exam from 2012. As I said, this is a calculator active set of problems, so make sure you have your calculator by your side so you can follow along. Let's dive in. Now this first problem, number 88, is a word problem. It's a related rates problem. We can see that because we are asked in the context of the word problem about a rate. What rate is this shadow lengthening as someone walks away from a street lamp? For related rates problems, whenever possible, it's always a good idea to draw a diagram. So here, you don't need to add all this artistic glitz and glamour like I am, but it doesn't hurt, okay? So we have a street light. It is 15 feet tall, and it is casting a light down. It is producing a shadow. So this person is apparently 6 feet tall. And we have a shadow being produced. So this beam of light is hitting, just passing over this person's head to produce the tip of their shadow. And we want to know, as this person who is walking away at a speed of 4 feet per second, at what rate is the length of that shadow increasing? Okay, so the way into a related rates problem is to look at the information that we have that we're given and figure out how to attach it to the diagram. So we've got the 15 feet tall. We have the 6 foot tall person. And the thing we don't have in the diagram yet is this 4 feet per second. So that is the speed at which he is walking away from the street lamp. Okay? So if we have a variable that represents the distance he's walked away from the speed lamp, let's call it x, we know that dx by dt is 4 feet per second. Okay. Well, we want to know something about the shadow. We want to know how quickly, at what rate, the length of the shadow is increasing. So let's introduce a variable to measure that. So here is my shadow. Let's call it h. Now, with this setup, we want to know what dh by dt is. So I've captured all of the given and desired information in this diagram. The one thing we need to do now is use our diagram to set up some kind of equation or formula. Once we have our equation or our formula, we can differentiate with respect to time and then substitute in to find the quantity that we want, namely dh by dt. So here, these often boil down to geometry problems, and indeed, what I see in this diagram is a couple of triangles, right? If we've done enough related rates problems before, we've probably seen this pair of triangles before, this setup. Let me remind you. So we have this large triangle formed by the streetlight as its vertical side, but we also have this smaller triangle formed by the person. Now, the key about this pair of triangles is that they have to be similar because they both share this right angle pairing, and they actually overlap at this angle right here. Okay? So because two of their angles, their angle pairs match up, because by the angle-angle similarity criterion for triangles, cast your mind back to geometry, we know they have to be similar. And for similar triangles, I can always compare matching sides and know I have a proportion, okay? So in particular, if I look at the ratio of the horizontal side to the vertical side, that should be the same no matter what if I'm looking in the small triangle or the large triangle. So let's look. In the large triangle, the longer leg of the triangle is x plus h, is that full horizontal distance. And the vertical side, the shorter leg, of that large triangle is 15. That ratio should equal the ratio of the longer leg in the smaller triangle. That's just plain old h. If I take the ratio of that to the other side length, namely 6. So this is my equation that I've written down using the geometry. I can maybe tidy this up a bit, but then ultimately I'm going to differentiate both sides with respect to t, and that's going to give me an equation that I can algebraically solve. So let's just cross multiply here. So I'll get 6x plus 6h equals 15h. If I gather terms, this will give me 6x equals 9h. Now I'll just differentiate both sides. So 6x will become 6 dx by dt. 9h will become 9 dh by dt. And now I can just substitute in the fact that I know dx by dt is 4. So I get 6 times 4 equals 9 times dh by dt. But let's just divide that down to get that dh by dt is 24 over 9. We could type this into our calculator. We could just simplify this. This is going to be 2 2/3. When I'm rounding to my 3 decimal places rather, I will get 2.667 as my correct answer. That's choice B. Nice work. Let's look at this next problem, number 89. Now we're told that a particle is moving in a straight line. We're given an expression for the acceleration at time t, and we want to know what the velocity of the particle is at time t equals 3, given that we know the initial velocity at t equals 0 is 5. Now this classic calculator problem, because what we're going to apply is the net change theorem. Okay, and what this all comes down to is integrating a rate gives you the net change. So what we see is one general way to think of the net change theorem is we have an initial value. We're going to add on the integral of our rate of change with respect to time. And that should equal our final value. This is true in lots of situations that we look at. Is particularly true in this problem. So let's say we're going to apply this here. So the initial value is going to be v of 0 at time t equals 0. The good news is I know what that is. I know that it's 5, so I can substitute that in a second. And then, crucially, the rate of change of velocity is just acceleration. So I'm going to integrate from time t equals 0, the initial time, to the time that I'm interested in, which is t equals 3. So those are going to be the limits of my definite integral. And all I'm going to integrate is my rule for a of t with respect to time. Now, v of 0, as I said already, I can replace that with 5. So all I have to type into my calculator is this, because remember, one of our calculator skills is being able to calculate a definite integral. If you're a bit rusty on that, if you're not sure exactly what you need to be able to do on your calculator, I'll put a link in the description to my calculator skills video. In it, I run through the 4 crucial skills you need to be able to do on your calculator. On the AP Calculus exam, they come up every year. If you master those, you're going to be in great shape for the calculator portions of the exam. I'm going to assume for now that you're fairly comfortable with using your calculator to find definite integrals. So let's pull up our calculator. So I want to calculate 5 plus the definite integral. So I'm going to hit Math, entry 9, and that pulls up my definite integral. I'm going to calculate from 0 up to 3. And now it is this rule they've given me for a of t. My calculator is using the variable x just for simplicity. So the rule for a is, it's a fraction, so it is the variable plus 3 divided by the square root of the variable cubed plus 1. And what I get, the 3 decimal places, is 11.710. Is that one of my answers? Indeed it is. It is answer choice E. Good job. Let's talk about this next problem, number 90, because for it, your calculator is going to be no use, because looking at it, what would you even type in? You're given an abstract integral being equal to 10, and you're being asked, what else must be true? Well, I don't know anything about f. I can't work with f. You haven't told me anything except this definite integral. So we need to scratch our heads and think about what is going on here. So what I do notice is that in the integral they've given me, the input is 2x. That's a bit weird, right? That kind of stands out to me. And I notice that in all of my answer choices, the variable is a single letter, t. My dx has changed to a dt. So if I'm comparing those integrals, I might think this looks a bit like integration by substitution, right? Certainly I'm using a different variable in the integrals. I don't know if they're related in any other way, but that hopefully sets up our integration by substitution antennas. Now, the AP question setters love this kind of problem because they know that you students spend hours and hours practicing all of your different integration methods. And so if they give you an integration that requires integration by substitution, you're going to load up the software, turn the handle, get the right answer. But this requires a little bit more conceptual understanding of what's going on underneath the hood with integration by substitution. So they love questions like this. Let's see how we're going to tackle it. Well, it looks like to get this integral to look like one of the ones in my answer choices, I need to replace 2x with t, right? So let's try that as a substitution. So let's say that we're going to let t equal 2x. Like any other substitution problem, I'll take the derivative of both sides. I just get 2 on the right-hand side. And now I'm going to tidy this up. And in particular, I'm going to say that 1/2 dt is equal to dx, because you can see in this integral, I've got dx by itself. So I want to replace the dx with something directly. But notice we also have our limits of integration. So we need to figure out what those are once I change from a dx integral to a dt variable. So let's set up a table of values. So my limits in terms of x are 6 and 12. T, right, the rule for t just doubles x. So 12 will double to 24 and 6 will double to 12. Now, we're in business. Let's do the substitution and see what we can learn from it. So I know that, and I'm just going to sort of shove this on the front because it will help me later, that 10 is equal to this integral. So the integral from 6 up to 12, f of 2x dx. Well, let's see. I have that dx quantity right there that I'm going to replace with 1/2 dt. I have this 2x quantity that I'm going to replace with just plain old t. And then I have these limits, 12 and 6, that I'm going to replace with 24 and 12. So when I do this substitution, 6 goes to 12, 12 goes to 24, 2x goes to plain old t, and dx gets replaced with 1/2 dt. Okay, so where are we? This starts to look like the integral in question, right? It's 12 up to 24, at least some of the integrals have that as the limits. F of t, I've got 1/2 dt. Let's just pull that out the front. 12 up to 24, f of t dt. This is fantastic news because this integral certainly appears in my answer choices And now I have an equation that says that 1/2 of that integral is 10. So let's just multiply by 2 all the way up here to get that 20 equals the integral from 12 up to 24 of f of t dt. Is that one of my answer choices? Well, we're in luck. Yes, this is indeed the integral that I have highlighted in yellow, and it is equal to 20, which is the result of multiplying 10 by 2. So the correct answer is answer choice B. Well done. Okay, next problem, number 91. This one takes some reading and some thinking. We're told that f is a polynomial function, and we're given some values of its first derivative, f prime, in this table. And then we're asked which statement must be true. And the way into a problem like this for me is to sketch a quick graph, because that lets me start experimenting, trying to work out which of these statements might be true, which definitely can't be true, because I find a counterexample, that sort of thing. Okay? So let me get these 5 points plotted. So I know that I've got x values -2 and at 0, at 3, at 5, and at 6. Let's plot these points. So when x is -2, I get a point at 3. When x is 0, I have a point at 1. At x equals 3, I have a point at 4. At x equals 5, I have a point, oh my goodness, it's off my graph, but that's okay. It's just a sketch. And at x equals 6, I have my output of 5. Okay. Well, let's now take each statement in turn and see what we can figure out here. So each of these statements is saying something about a property of the function f, but we have information about f prime, its derivative. So each of these properties we can translate into a statement about f prime, and that's how we'll actually make some progress with this problem. So looking at our first statement, we know that f is supposed to be concave up. That would mean, if we remember about concavity using our second derivative, that f double prime is positive, but I can detect this using the first derivative. Okay, f being concave up means that f prime should always be increasing on this interval. Well, you can see that f prime, if I draw some examples that sort of hit the points that it's supposed to, if that is my graph, y equals f prime of x, it's perfectly possible for f prime to hit those 5 points, but for it to not always be increasing. In fact, it has to decrease between some of these points for us to hit those points, because we're a polynomial, and so we have to be continuous. We have to have long decreasing sections. So because f prime must occasionally decrease, f must occasionally be concave down. So that is not one of our possible answer choices. Now, let's skip over B because it's kind of scary looking, and you'll see why I want to skip over it. But maybe I'm a bit intimidated by B because it talks about inflection points, it talks about 2 or more. I don't want to deal with that right now. Answer choice C says the function f is always increasing. Okay, so if f is always increasing, that means that f prime should always be positive on this interval. F prime, the sign of f prime detects whether f is increasing or decreasing. And it looks like, from these 5 data points, plausible, because they are all positive values of f prime. But the table doesn't tell me anything about what I'm doing in between these points. Okay, it's perfectly possible I could draw a graph of f prime that dips below the x-axis and becomes negative. So it's possible that f prime is negative, but still manages to hit these 5 points in the table. So that would force f to sometimes be not increasing, be decreasing. So this does not have to be the case that a function f is increasing. It could occasionally be decreasing. Let's look at our next answer choice, D. This is proposing that f has no critical points. Okay. So a function f has critical points if f prime is 0 or does not exist. Right? If you find an x value that returns 0 or does not exist, then that gives you a critical point of the function. Well, this is a polynomial function, so its derivative always exists. But we saw an example already, right, of an f prime that hits these 5 points, but is occasionally 0. Okay? So each of these zeros of f prime would give me a critical point of the function f. So this needn't be true. It needn't be the case that f has no critical points, because we cooked up an f prime that can be 0. So it's not answer choice D. Let's now look at this answer choice E. It's saying that does function f have to have at least 2 relative extrema? Well, relative extrema occur when f prime changes sign, either from positive to negative or from negative to positive. Does that need to happen for an f prime that travels through these 5 points? Well, no. Right? I could have an f prime that very happily hits these 5 points, but stays entirely above the x-axis, stays entirely positive, never changes sign, and so f might have 0 relative extrema. So answer E cannot be true. So that one that I skipped over because I said it looked kind of intimidating, by process of elimination, has to be correct. If this was an exam situation and we were under time pressure and we were confident in scoring out those first 4, we'd probably circle B and move on. But since I have you here, let's run through why answer choice B has to be the correct answer. Well, it's talking about f having 2 or more inflection points. So let's see here. An inflection point occurs. That means that f prime changes from increasing to decreasing, or decreasing to increasing. Because remember, an inflection point is where concavity changes. Okay? Going from concave up to being concave down, or concave down to concave up. Usually we detect concavity with f double prime being positive or negative. So if the concavity changes, the sign of f double prime is changing. Well, at the level of f prime, if the sign of f double prime changes, the increasing decreasing behavior of f prime changes, because the derivative of f prime is f double prime. So let's have a look here. So if I have a function, it has to do something like that for f prime, because I start and I travel down towards y equals 1, and I need to swing back around to get back up to y equals 4. No choice about it, because I'm a continuous function, I'm going to have to do that swing. And similarly, I need to go all the way up to y equals 7 and then swing back down. Okay? So you can see I have a change in behavior of f prime. F prime is decreasing, and then it has to start increasing. It might do something a lot more complicated, but it has to go from decreasing to increasing to hit those 3 consecutive points. And similarly, up here, I have to go from increasing to decreasing for f prime in order to hit those 3 points like that. So because my decreasing, increasing behavior changes at those 2 separate points, and it has to, there's no way around it, concavity has to change at those 2 points. And so in particular, those 2 points must be inflection points. There could be more, but these 5 data points force f to have at least those 2 inflection points. Quite a lot of thinking there, but we got there, so well done. Let's look at this final calculator multiple choice problem on the 2012 exam. It is number 92. We are told that we have a region R, bounded by y equals x squared below and y equals root x from above. In a problem like this, if you're not sure what to do, a diagram is always helpful. Now remember, we can figure it by inspection. That intersection point is going to be 1, 1. And so now I have this nice region R nestled between these two curves. Now what we are told, this region R is going to form the base of a kind of weird looking solid. Okay, it's the base, and if I take cross sections down this solid perpendicular to the x-axis, what I'm supposed to get for the cross section is a square. Now, I can't really visualize what this solid looks like. If you can, very impressive, okay? I can kind of see it if I close my eyes and think about it a lot, but the beauty of calculus is I don't need to perfectly visualize what's going on to be able to calculate and work with this object. So, what are these cross sections? Well, it says that if I take my knife and slice this cake perpendicular to the x-axis, I'm supposed to get a square slice out of the cake. So, okay, I'm going to sort of have the square come out of the screen at you. And just for emphasis, I'll shade it blue. So that's one cross section. I could do another one maybe up here. If I slice at this point on the x-axis, again, I'm supposed to get a square cross section. It's going to come out of the screen towards you like that. Now this diagram is not really helping us solve this problem. You don't need to draw this on the exam under time pressure, but hopefully it's helping you sort of visualize what's actually going on in this problem and help you get a little bit more understanding. Ultimately, what we want to do is calculate the volume of this solid. And the key thing here is, here we are interpreting a definite integral as measuring an accumulation. Okay. Here, the solid is made up of an accumulation of cross sections. As x travels from 0 up to 1, this solid is swept out by all of these square cross sections that I keep getting when I slice down. Now, the beauty of definite integrals, the beauty of calculus, is that I can figure out the volume of that solid by integrating the area of those cross sections. So I want to integrate from 0 up to 1 dx, the area of the cross section at x. If I add up all of those slices, it will give me the overall volume. Okay, well, how am I supposed to figure out the area of a cross section? Well, the good news is it's a square. So if I know the side length of the square, I know to just square it to get the area of the square. How am I going to do that? Well, let's say I look at this particular cross section at x on the x-axis. Well, what is this side length here? Right, this side length right here, how do I find that? Well, I can take it as a difference, right? Because this y-coordinate, it lies on the graph y equals root x. So that is that y-coordinate. This y-coordinate is x squared, right? It lies on the curve y equals x squared. So that difference there, that side length of my square, is going to be root x subtract x squared. Just taking a difference there to figure out the length of that segment. So what I'm going to type into a calculator is the integral of 0 up to 1. I want the area of that square, so it's going to be the side length squared. My side length, I just figured out, is root x minus x squared. So let's pull off our calculator and calculate this different integral this time. So again, I'm going to hit Math, entry 9. I'm integrating from 0 up to 1. The quantity I'm integrating is the square root of x minus x squared, and it's that entire difference squared. What do I get? I get 0.129 to 3 decimal places. Oops. 0.129 indeed. So that is answer choice A. There we have it. Okay, there we have it. The final 5 problems on the 2012 multiple choice section. How did you get on? Let me know in a comment which question you thought was trickiest. As I said, if you're a little bit rusty on your calculator skills, I'll put a link to my calculator skills video. It runs through the 4 things you need to be able to do on your calculator. I'll also put a link to the full multiple choice playlist I've got from the 2012 exam, so you can run through them in order. Apart from that, I will just say good luck, thanks for sticking with me, and I look forward to seeing you next time.